right, next we have Keith Graham from Codasip.
Hello, thank you very much for coming. So this is actually a culmination of 3 research projects within Codasip. One is on AI, the second one is on DSP, and we're going to be focusing on fixed point. And the third one is our new technology called Fusion, where we're enabling people to actually customize a core, but not violating the verification of the core itself, which means that companies that don't have a verification team for processors can now have custom compute and have a custom core. So let's take a look at a few things. So we decided let's do a full application, not just an instruction. So we decided, okay, what would be a good example of trying to do something? And I really like that OMIDA presentation beforehand. AI at the edge, because that's what we did, AI at the edge. So what we're going to do here is create an anomaly detection IC. And the idea is, as a company, my boss has came to me and said, you know what, we sell sensors, but I want to go up the value chain so I can sell more higher value product at a higher ASP and make more money for the company. So that sounds great. So we're going to take our sensor IC technology, combine it with a microcontroller that actually is going to do DSP operations and AI operations to do anomaly detection, and now have a new IC called anomaly detection IC that is a smart sensor, and therefore we can actually increase the value chain. But when your boss tells you that, and he gives you a few of the criteria, you walk away from that meeting. I'm really excited about doing that, but there's a few things that might seem impossible. You know, we're modeling we need 120 million cycles.
Just for a second.
Yeah. Okay, so we're modeling we need 120 million cycles, but we're only allowed a 25 megahertz operation because we want to work at 40 nanometers to be on the same technology node, which is the 40 nanometer low power, to match our sensor. So that's the first problem. Okay, gosh, that's impossible. Well, through customization, we're going to be increasing the performance in this particular work that we did. We ended up at 4.36x increase. But we did some other advancements, and so we're actually down to 16 to 18 megacycles per second we need to do the DSP and AI operation. The second thing was, well, I'm going to say we know RISC-V, but we just want to model this as another company. No expertise in processor design. Well, through our new Codasip Fusion product, the interface to actually program or customize the core is a software and programmer's model. It's not a processor engineer model, but a software program. I used to teach embedded software at the University of Colorado, and if you're an embedded software programmer and use that model, you use the same model and you can create instructions. I don't need to know anything about the microarchitecture of the processor. I have a software model that I want to add to my processor to accelerate, to create new instructions. Second of all, once again, we know about RISC-V, but assuming that the company does not have, or the engineer doesn't have a lot of experience, you don't need to know anything about RISC-V. Because through this interface we have, we will actually generate the opcodes through the custom space that's provided by RISC-V to you automatically. You say, I want this type of instruction, we will generate the opcode. You don't even have to know the opcode at the end, because when you actually use it in your software model, you just say, here's my instruction, and it might be some particular AI accelerated instruction, and will automatically fill in the opcode for you. And the last one is little experience or no resources for verification. You know, we're a company that modeled in this research project. We're an SoC company. We don't have a verification team for processors. So we're choosing the Codasip Fusion because we're guaranteed that the processor core is verified, and we cannot harm the core through our bounded customization. Now, the first thing we did was, I'm working on a paper now where I think the future processor engineers is going to be the software engineer. It's not going to be the processor engineer. The reason why is who understands the algorithm of the application? It's the software engineer. And so we need to get them involved in deciding the new software-hardware interface. So bringing in our AI team into this problem, we looked at the GEM inner loop. We needed 8-bit resolution for the AI, and so we created a new instruction called AI Mac integer unsigned. So from this particular Mac operation, we created a new instruction, and now we're actually doing on a low-end processor effectively 1 Mac mole per clock cycle. So we're becoming very efficient. We actually became so efficient that we overshot our budget, so we're actually running more efficiently than we thought, and our AI part is much smaller on the length of time. So we're able to take this instruction and actually, through a programmer's model, add it right into the core. Now, I was on a call with our AI team, and literally he was going like, how do I actually optimize this code? Because the arrays need to be aligned so that I have single cycle loads. And I go, well, I can do it for you. I can create a new instruction to actually handle single cycle unaligned loads. And so we created that instruction in about 2 hours. And then all of a sudden, he no longer the software guy. I made his life easier, right? Because it does auto aligning for him. And we're doing single cycle unaligned loads with a 32-bit interface. So between the last 2 items, we've been able to vastly improve I think we're getting like at the application layer approximately 6x. But really the key thing here is take a look at Fusion. So Fusion enforces a set of rules. For example, you cannot actually modify any of the core files, because if you could touch one of the core files, then we cannot guarantee that the verification of that has been upheld, right? So we enforce the rules that you cannot actually modify the core files. Now, there is a particular space that you work with, and you're only allowed to work within that space. So within that space and with the basic templates, you can add your instructions. Now, you can see what type of performance we're getting in the GEM loop. So depending upon the size of the matrix, we go from a little over 3 to up to close to 8x. We're really, right now, with the current design of this core that we used, which was the L110, we're actually memory bound at 10x or 8x. So that as a summary, if you're experienced with the tool, you don't need to know anything about computer architecture. You don't need to know anything with RISC-V. In about a month, you can add like 40 instructions to accelerate your particular application. It's roughly 3,000 lines of code that I wrote. And through the bounded customization, I've guaranteed the verification of the core. So you can almost imagine after about a month worth of work, we've been able to improve the performance. Let you know at the application layer, we're improving the performance by 4.36. But even more than the application performance, we have actually reduced the power of the application by 7x. So, which is really amazing. That surprised me because, one, by adding functionality, you think I add more hardware. But I actually made the hardware run more efficient. And so all the power numbers, just to let you know, are actually post-synthesis. So we actually ran post-synthesis software. So these are not made-up numbers. These are actually RTL data. So our work here shows that you could very easily, very quickly, with low risk, what we call microaccelerators. When I say microaccelerators, we're talking about anywhere between 5 and 10x performance improvement at the application layer. And so I think the key thing here was it was a lot of fun project. There I see a couple other people here from the team. But if you really want to, I didn't think I could actually do the demo here, but we are running the demo. It's sort of in the middle of the expo hall right across from where the food is served. But we can actually show you a little bit more detail of what we did at our booth. There's also, my last thing I'd like to show, I have a blog here that came out 2 weeks ago. If you go to the Codasip website, you can find. But it's basically going in a little bit more detail of what I'm talking about, where there's the new paradigm is the Fusion product, which is a combination of our EDA tool and our core. But the more important thing, we're moving forward where the software engineer is going to be the future process engineer. So thank you very much for your time. Well, thank you very much.
Thank you, Keith. Thank you.